And we're back with a hopefully quick tutorial on petroleum boiling. Now, first off, before we get into the nitty-gritty of doing it, I want to concentrate on the benefits for a moment because I feel like a lot of them get missed. The first thing is, it doesn't just provide you with power, it provides you with food. The reason being, when you burn petroleum, it gives off carbon dioxide, and that carbon dioxide can be used to feed slicksters. Also, this is perfectly sustainable. We'll go into that in a bit, but this does mean you can produce about 9.5 kilowatts of sustained power constantly. You can feed almost 75 slicksters, which is almost enough to feed 50 Duplicants barbecue. Say, I wouldn't go quite 50, say 45. And the whole thing is perfectly sustainable forever. So 9.5 kilos of sustained power and enough food to feed about 50 Duplicants for as long as you could possibly want, and it's all obtainable early game without any space materials, using either copper, gold, or aluminum. And the reason it's so sustainable is oil wells. You take one of these oil wells and you dump a kilo of water into it and it spits out crude oil. 3 of them won't quite produce 10 kilos of crude oil per second, but it works out about 9.5 kilos of crude oil. Then you take that, you dump it through your petroleum boiler to get all your wonderful benefits. And then, as well as that, the petroleum generator kicks out 750 grams of polluted water. Now, polluted water, you can sieve it or boil it to turn it into clean water. And it takes you 2 kilos of... It consumes 2 kilos of petroleum to make this. Doing the math on this, it means you put in 3 kilos of water in here, and you get out 3.25 kilos in return. So it's a water-positive process, a power-positive process, and a food-positive process, and it lasts forever and ever and ever. That's why it's so powerful, that's why it's so useful, and that's why it's one of my favorite forms of energy, because it solves multiple problems simultaneously, and it's very easy to achieve. For this reason, I consider it, power-wise, it's not as good as, say, sour gas boiling, which gives you natural gas, but on the plus side, it gives you far more carbon dioxide to feed your slicksters, which means you have a sustainable food source. Now, because it will provide you with 75 slicksters, an extra 3/4 of a kilo of water, and it provides you with power, one of the most common things I hear people doing is they turn these off and turn them back on again when they don't need any more petroleum. That's the wrong way to think about it. You're thinking about it the same way as you do, say, no, I don't have one left, a coal generator. Coal generators, you turn them off when you're not using them because you want to save coal. In this instance, you don't ever want to save petroleum. You do keep a stockpile. I do keep a stockpile of petroleum just for if there's any interruptions in flow or any complications. So that's there as necessary. However, the moment all of this fills up and backs up to here, an automation signal is sent, and this tells the petroleum generators to turn on and start burning off the excess petroleum. The reason being, you want that carbon dioxide to feed your slicksters, and if I'm burning off that petroleum, then I'm producing an extra an extra 3/4 of a kilo of water at the same time. So turning off the petroleum boiler and not using it when you have 3 oil wells to feed it is actually a bad thing. You're decreasing the amount of resources you're bringing in. So turning them off is usually a bad thing to do. Just saying. Now, building these, there's different ones depending on what type of materials you're going to have available and what type of volcanoes you're dealing with. First thing to explain on these is the counterflow heat exchanger. Don't worry, they're not that complicated. It's fairly straightforward. The crude oil comes up here and it's going through these radiant gold pipes. And it snakes its way all the way to the top where it gets dropped in and heated up in our heating area. At that point it turns into petroleum, and as more and more crude oil is dropped in, it forces this petroleum out and down the counterflow. That's the counterflowing part. And as it counterflows down, the two of them exchange heat. And the petroleum starting off very hot at 400 degrees, and the crude oil coming in, I think this one's about 80. Yeah, this is 80 degrees. So as the two of them counterflow past each other, they keep exchanging heat. And because there's such a long stairs and they're all the way spread out, they keep dumping heat back and forth so that by the time the crude oil gets to the top, it's preheated to 385 degrees. So it's gained over 305 degrees in temperature on its journey up the counterflow. So when we get to the top, it only takes a tiny little bit of heat, well, 15 plus degrees of heat, to just push it over the edge to turn it into petroleum. The reason you need this is you can't just, if you're just trying to straight boil 80-degree crude oil into petroleum, it takes an enormous amount of heat energy. You would quickly drain all of the magma from this tank, the volcano would run out, your petroleum boiler would stop running, and then you would run out of petroleum. Therefore, no slicksters and, no power. That would be bad. The whole point of a petroleum boiler is to make the design as resistant as possible and to last as long as possible. It should never, ever need to stop. If it needs to stop, then you're not getting those resources you want, which means you can't depend on that slickster food, you can't depend on that power, and you can't depend on getting that extra water. The next part to explain here is this section over here. This is the magma dropper, and it allows us to drop down 2 tiles of magma. Now, there are ways you can use debris to boil petroleum. Unfortunately, they're not quite as efficient. The reason being, you can't get temperature out of debris nearly as efficiently as you can out of a solid tile. So what I like to do is let the magma form a solid tile and then extract the heat out of it. This will allow me to drain the heat out of it down to about 430, 435 degrees, depending on the design. So you notice all this igneous rock has been drained down and drained almost dry of heat. If this was debris, I'd be lucky to get it down to 480 degrees. This usually allows you to absorb to drain the most amount of heat out of your igneous rock, well, your magma / igneous rock, and get the most life out of your boiler. The way it works is not the simplest, but not the most complicated. Now, excluding the plumbing, it's just a one pipe going one direction and the petroleum flowing down the other, this requires a little bit of automation to get it working right. Ignore this little spike over here. This is a reset toggle, this is a temperature sensor, this is a filter gate, and this is a NOT gate. So what I'll do is I will fast forward this until the device is about to cycle, and then you can see it in action. So I may have hastily applied just a little bit too much chilling to this using the heat gun. Once the temperature goes below 435, which I accidentally decreased to 365, oops. Once the temperature gets that low, the automation wire here sends a signal. That signal goes up here and it activates the mining drill. That mining drill is the only thing that activates for the time being. Well, okay, that and the door. So the door opens down here, the mining drill activates, and this filter gate stops the signal from progressing for 20 seconds. So for 20 uninterrupted seconds, this mining drill will just go ham on these blocks. So as you can see, it's actually counting down there, and you'll see the bar going across. Once it hits to about 20 seconds, a time that's been specifically picked because about 2 seconds before the 20-second mark, this has finished mining out the area. What this will happen is let the signal pass on. The signal will go up here, open this door, pass through this NOT gate, which flips it to, well, it's going to flip it from green to red, which will close this top door. At the same time, this will allow the signal to pass on through here and hit this reset button, causing this door to close. So to sum up, this door will open, this door will close, and this door will close. So this will close, and the middle door will open, dropping in our fresh batch of magma. And observe. Now, once that drops down here, that's going to hit this temperature sensor. And when it hits this temperature sensor, it's going to raise the temperature back up again. And when the temperature gets raised back up again, this resets the whole system, as this will tell everything to shut. So the whole system will cycle itself. Watch. There we go. That door closes, that door opens, and now we're right back to where we started. This all just makes sure that the magma cycles through, we get the heat when we need it, and when we're finished with it, it gets spit out the bottom. You may want to think about recycling this igneous rock. Personally, I don't care. You can use it to feed hatches, but I did the math on it once. I think it was about four hatches. You could run about 4 hatches on it, which, yeah, I suppose. I wasn't bothered putting in the extra effort. Considering the amount of power, food, and resources you get out of it all already, putting in the extra effort to take care of that wasn't a bother. Now, for another very important question, why is the counterflow as long as the counterflow is? Well, that's down to materials. This is gold. So as gold, it has a thermal conductivity of 120. A radiant gold pipe has thermal conductivity of 120. However, the new introduction of aluminum has changed things quite a bit. Aluminum has a thermal conductivity of 410. It's almost as good as space metal. And both of those materials are available early in the game, which affects the petroleum boiler designs. So we'll just start with gold. Gold has, well, weaker thermal conductivity. Also, copper is identical, so gold or copper can be used for the piping in this. It's your choice. But these have weaker thermal conductivity, which is why it has a 4-stair length. Now, the reason we're picking 4-stair lengths is because this is a regular volcano. If you take all the volcanoes that are out there, this here is the Tools Not Included map website, and I'm looking for a volcano that at most is outputting 760 grams of magma a second. None are in existence. However, if we go to 0.77, they do exist. One of them. This means the weakest a volcano can possibly be, or a regular volcano can possibly be, is 760 grams of igneous rock a second. And if we go to minor volcanoes, so here are minor volcanoes, the weakest you can possibly find is 380 grams a second. Now, these are the absolute minimum values you will ever have to deal with. And the reason this is important is when you're playing this game, you want to account for the worst case scenario. Taking that knowledge, we just have to figure out how to make a boiler that uses less magma per second than the worst volcano could possibly output. That means no matter what regular volcano you stick this petroleum boiler on, it will work. Whether or not you're able to analyze it or not doesn't matter. What type of volcano it is, how much it outputs, you don't have to care about it. You just stick one of these on it and you're done. However, the type of volcano matters and the type of materials you have access to matter. So there are 4 designs on this map. 1, 2, 3, and 4. This one over here is the gold/copper section and a regular volcano. Based on this size, this design will consume 635 grams of igneous rock or magma per second, meaning this will work on any regular volcano you care to name. This one over here is designed for minor volcanoes and also it runs on gold or copper piping. This exact size heat exchanger will consume 383 grams of magma per second, meaning this will work on any minor volcano variant you could possibly find anywhere at all. Then you've got this down here. These ones are the aluminum section. This one has not been enabled yet because I want to show you how to do that. This one here is the minor volcano variant, and it consumes 375 grams of magma per second. Now, I've left this pipe segment broken because I should really demonstrate one of the wonderful quirks of this game. This here is coming in at 401. The reason when the fresh magma goes in here, sometimes this is going to crack. So what you can do to stop that from happening anymore is you can replace that with an insulated pipe. It's also one of the reasons I usually leave 2 tiles of a gap in here. You can get your duplicants to come in through here, and a simple thing to do to get it to work: put a little drop of liquid right there and put a little gap across the top. This can be handy because if we'll check here, there's a whole bunch of oxygen this side, but it hasn't managed to force its way through, and your duplicants can navigate across that. So if we just stick in a duplicant there, and we'll tell them to move to over here. Oh, they can't get across there. Sorry, 1 second. Ladder segment. They can get back and forth. No, I don't want to leave them in there because they'll exhale some carbon dioxide. Anyway, done and dusted. You should make sure, of course, to have atmosuits before you even think about getting involved in this. Most of the breakages you're going to get are going to happen on the last few segments around the top stair, so that's why I usually leave this 2-tile gap so my duplicants can get in and out. The other ones you can leave a 2-tile gap if you want, but it will make the design bigger. It just will allow you to service it more easily if any issues arise. This design consumes 375 grams a second, and this final design consumes 596 grams a second. These ones are still works in progress. Aluminum is still quite a difficult material to work with. It provides so much heat exchange so quickly, it has a tendency to overheat the petroleum just a little bit, especially when fresh magma is dropped in. So let's fire up one of these designs so you can see how it works when you're first starting it. The first thing you're going to want to do when you start up the system is throw out a little bit of crude oil first. The reason being, you want to get this temperature sensor in range of some crude oil to get started. Otherwise, it's going to detect minus 273 degrees because there's no liquid in here, or no medium, nothing for it to interact with, so it's always going to detect absolute 0. While that's filling up, we're just going to keep an eye on this here, and we're going to disable the building just as the crude oil gets to the level where it's going to trip the sensor. Once that happens, we hit the disable building button. That should fill up now. If we don't do this, we can't open that door. Well, let me explain this better. If we dropped in the magma now before we put in the crude oil, what would happen is the door here would stay constantly engaged. We wouldn't be able to disengage it, and this metal plate would heat up to over 1,000 degrees, which means when the crude oil came in, it would hit the plate and instantly flash to sour gas. So we're just doing a little bit of a pre-dumping of oil in there just to make sure everything's ready. As well as that, make sure you've got your automation in place. I didn't have the automation wire in place and had to reload this video. Yeah, so I'm going to take my own advice on this one. So all the automation wires are in place, and this hydro sensor here is the kickstarter. It's what flips on the system. So we activate this, it cycles that, and lets the magma drop in. We then turn it off, and we deconstruct it. And you'll notice there that magma is immediately dumping a lot of heat into that crude oil, and the crude oil flashes. There we go. Now the system's ready to be turned on fully. So we'll enable this building. Petroleum will start going up here, flowing over, and the system should be good to go. And that's it. You will never have to touch this again. It will keep functioning forever and ever and ever. There is only one last thing that needs to be done to ensure that this system is completely stable, and that is to do with the mining drill. Now, you notice the mining drill there is 83.8 degrees. I did a bit of preheating on it before this game started, and you'll notice that the temperature of the crude oil is only 29. So why is nothing is transferring heat to that? Because it's in a vacuum. Because it's in a vacuum, we need something to transfer the temperature to it. Now, normally what I would do is I would say fill this area in like this. And then I would pump in some oil in a pipe, and then I would crack the pipe open right here by deconstructing it, and it would drop 10 kilos of oil on top of this spot. Then I would just mop up the oil that ended up down here, cart it away, and then deconstruct this brick afterwards. Now that's covered more in something we'll get around to later, but for just this, we'll use Sandbox mode. We will sample that section up here, and we will brush it down here. Oh, nope, that's too big. We'll brush it down there. And then what will happen is you'll watch the mining drill immediately drops in temperature. It's now down as far as 34, yeah, so we're good. Okay, we'll deconstruct that. Now, you'll notice down here there's a little blob of igneous rock that ended up on top. Sometimes this happens. This can be a huge problem. What sometimes happens is you'll have a building queued up and it will require a little bit of igneous rock, and a duplicant will come running in here because they can get in here. It is a serviceable part, and they will grab that igneous rock. Unfortunately, when duplicants are holding, say, 1100 degree igneous rock and they walk through something, they transfer heat, and there's a possibility they can transfer heat to this crude oil blob and turn it to sour gas. This has also caused me problems in the past. So do yourself a favor and wall this in, or put in a door here and restrict permission so that no one can get in. Just make sure no duplicants can get in here and you shouldn't have any problems. This newer design, there was an older design that had constant problems with that flashing. This newer design, I haven't had any issues with it yet. Well, okay, I pumped water into it, into the crude oil supply once. But barring my own mistakes, this thing has been rock solid and I've never had any problems with it. To sum up on these 4 designs, the save game file is included, by the way. This here is for if you have gold or copper piping and you don't have access to aluminum. This will work on a regular volcano regardless of its output. This will work on a minor volcano regardless of its output. If you do have access to aluminum, then this design will work on a regular volcano regardless of output, and this one will work on a minor volcano regardless of output. So these 4 designs mean no matter what situation you end up in, so long as you have a volcano of any type, you can build yourself a petroleum boiler. Now, what happens if you don't have access to a volcano? Well, in that case, there's geothermal. Geothermal is where you plug yourself into the magma at the bottom of the map and use that to power your petroleum boiler. Now, there's several ways to do it. You can just plug in directly. This was a save game file sent in to me by Gaharum, G-A-H-A-R-M-U-N. Yeah, I can't pronounce that. Gaharuman? Never mind. Anyway, what happens here is you have this big diamond window tile heat spike, and it's plugged into the magma. It goes in here, it hits into that door, and that goes back and forth. I watched this play out for 3 or 4 cycles, and I monitored the temperature that was down here of the magma. I figure out this should still last about 4,000 cycles. So this should keep going about 4,000 cycles before the heat in here gets low enough that this starts to have a problem. 4,000 cycles is longer than most people will ever play the game for. As well as that, you can replace your heat source with thermium aquatuner. This is a modified version of the exact same petroleum boiler from earlier. All I did was I ripped out the magma heat source, turned it off, ripped out the automation, and stuck in a thermo aquatuner made of niobium. Now, niobium overheats at 625, so I've set the temperature sensor in here to jack up the temperature to 600, and that's it. And that keeps injecting heat in here, and that heat just allows us to keep boiling petroleum. Now, this will, of course, cost you energy. This is 1200 watts to run this. I think the energy cost on it per second works out, on average, because it turns on and off constantly, is about 500-600 watts, depending on the length of your counterflow heat exchanger. Now, the cooling from this does have to go somewhere. If you don't dump the cooling into something, the supercoolant will stop working after a while. So I've had it dumped into just some water down here, and then as the petroleum is leaving the system, as in the exit petroleum here, I just run it through some diamond tiles that are touching the water, and that means that we actually add a little bit of cooling to our petroleum. It comes out as minus 122, and after passing by the actuator, it comes out at 88.5, so that's some very chill petroleum coming out of this whole system. You do not have to use supercoolant in this. You can get by with polluted water, and you don't have to use one made of niobium. You can use one made out of thermium, and you only need about 5 kilos of thermium from space, because you can use that. You can use the niobium you find to make thermium, and then you can grind up thermium to make more niobium to make more thermium. So 5 kilos, about 5 kilos of niobium from space will allow you to make enough allow you to make enough thermium to make as much aquatuners as you want. This combined within a regular oil biome type scenario, and you can make several dozen petroleum boilers and really just go absolutely crazy. This map here is where all of the counterflow testing for gold and copper was done. It's effectively just one lane longer, each one of these, and it was where all the testing was done to determine how much igneous rock each of these burned, depending on how long you ran them for. If you want to run your own testing, you can. All you do is you wait until this starts mining, and once it's hit a specific point, you note the time, note the cycle, wait until it does it the next time, and then you can figure out how much magma it's burned. Very boring, but if you're interested in that sort of thing, you can do lots of testing here to figure out what your magma efficiency rates. Save file included. One last version I forgot to cover is dupes can move magma around using a pitcher pump. Pitcher pump, so long as the top part of it here, this line up here, is not touching the magma, will not absorb any heat. So Duplicant can come along here and extract up to 8.7 tons of magma out of the system. And, well, okay, 200 kilos at a time, depending on the bottle emptiers. So you can use that to pull magma out of the geothermal section and dump it into, well, say this in here. So you can put several bottle emptiers along here, have this down in your magma biome, and transport magma in bottles and dump it in here. Just make sure none of it falls into your liquid locks or it could cause problems. That pretty much covers all the different ways you could either get magma, move magma, go to the magma, get it off a magma boiler, or hold out until you get some niobium from space so you can make yourself a boiler. There are several different variants of ways of getting to this. Now, as for building this, I did put up a tutorial before on how to put one of these together. It has a slightly different entranceway that was modified since. Well, I'll put a link to that if you're looking for a detailed description on how to build this, and it also contains a lot more other information. It's a lot longer than this nugget. The save game file for this is included, so help yourself to that. I have, of course, gone way too long on this video again. These nuggets are only supposed to be about 15 minutes long, and I'm way over budget. But I think we have covered just about all the questions that have come up in the comments over all of the episodes in series that I've done. But I'm pretty sure I've left a few out. There's always something, and I'll be kicking myself when I remember them. Anyway, I hope this was at least mildly informative for you, and do give petroleum boilers a chance. Once you build one, you'll never look back. After you've experienced the power of them, it's just impossible. Anyway, I hope you enjoyed, and good luck.